So everybody, my name is Said Abdullah, and I'm interested to present the results of a research we have done at Technical University of Munich under the chair of Traffic Engineering and Control. It's about hierarchical delay-based signal coordination for motor vehicle and bicycles. So first, a short review of the content of this presentation. We start with a brief of introduction, then we go to the case study of our area, and then explain how we got the traffic data. Then we explain how we built our simulation model by SUMO micro simulation software, and then the calibration and validation process for the network. Then it comes to introduction to signal coordination and what we have done as coordinating of the signal and a new algorithm of traffic control strategy for our networks. Then the results of this traffic control algorithm will be depicted in the results, and then we end our presentation with a conclusion. So there is a research question we have tried to answer, and that's how we can consider bicycles in a fair distribution of coordination strategy in a network among other traffic users. So imagine a network with multiple signalized intersections. From one side, we have bicycles, and from other side, we have also motor vehicles, and they have separated lanes. And now we want to know in which direction and to which traffic users we should consider, assign the coordination. To do so, firstly, we want to say why should we consider bicycles at all? Besides the benefits that we know the cycling as a sport activity, that it reduces the cardiovascular diseases, what is very important for us is also that the bicycle share in Germany is increasing, and we should also consider that. So in 2008, we had nearly 10% of mode share by bicycle in Germany, and in 2012, it has increased to nearly 14%. And it's predicted by some researchers and some growth rate forecasts that in 2030, the bicycle share would increase to nearly 35% in Germany. On the other hand, we saw that in majority of cases of signal coordination, only motor vehicles are considered. So then we go to the case study and the place we have conducted our study. So it's exactly situated in the center of Munich and includes nearly 9 signalized intersections along the Leopoldstraße and Ludwigstraße. This area has shown an increasing demand for bicycle because it's situated in a densely built environment with numbers of universities, schools, shops, and restaurants. This area also connects the north of the city to the center. And we saw a high varying of traffic volumes for both bicycles and motor vehicles. So the typical cross-section is also shown in the bottom, that the bicycle way is completely separated from a motorway. The traffic data was the basis for this study. We could install some cameras at some intersections to gather the data, and in some intersections that were not possible, we counted manually. We also considered the seasonal effects of our study. Therefore, we did our traffic survey in the summer to include the highest number of bicycles in our traffic survey. From this video recorded and manual counting, we counted the passenger car and trucks for motor vehicles and 2 types of bicycles as conventional bicycle and cargo bicycles for our study. Then we started building our simulation model. To do so, we have used SUMO as micro simulation software. So to the right, you see the whole stretches. We also used Tracy for traffic control strategy and controlling the controller, especially by the new algorithm. The traffic volume is statically distributed into the network by considering the turning ratios, and the cycle time of 90 seconds is implemented for all signalized intersections, as in current state. We have considered an evaluation period of 60 minutes and a warm-up time of 30 minutes by random seed. The information for signal time plans are also provided by the city of Munich. So then we calibrated and validated the network through traffic volume and travel time by different sets of data that we have gathered by video counting. And then we adjusted the parameters of a simulation model through calibration and validation, as well as through literature reviews. So to the right side, you see the table for adjustment parameters, which includes the physical and dynamic properties of traffic users. And a brief introduction to signal coordination. I'm also interested to do that. All of you know that signal coordination, if it's possible, it will increase the average speed of traffic users and increases the quality of traffic flow. At the same time, it also reduces delay and number of stops of traffic users. But here in this study, we had some other challenges too. So we wanted to include different types of traffic users. It means the motor vehicle and bicycles at the same time. So these traffic users have different physical and dynamic properties, means different speed, different acceleration, and different deceleration. In this case, how we can have a fair, or better to say, a weighted distribution of coordination for the network? To answer that, our signal coordination methodology should at least have 3 steps. It should consider the major traffic streams. It should distinguish the different types of road users, naming bicycle and motor vehicle. And it should also consider different weighting factors for different type of road users. So here you see the algorithm of traffic control strategy that we have built. This algorithm is based on comparing delay between motor vehicle and bicycles. To evaluate the network, we also define some measures of effectiveness like delay and number of stops. And we have also introduced some terms like interval length. This term means the length in seconds by multiple number of cycle time. This is what we have defined for this algorithm. And at the end, the evaluation of measures of effectiveness in interval length is also aggregated. So if I want to have an example to simplify the meaning, I would say if we, for example, take n equals 5, for example, in this case, if the delay, in this case, the interval length will equals to 5 multiplied by 90 or 450 seconds. So at an interval length of 450 seconds, if the delay of bicycle during this interval length is higher than the delay of motor vehicle, then the controller switches to the offsets required for bicycle coordination. If not, it switches to the offsets required for motor vehicle. And this coordination lasts for the next 450 seconds. And this process repeats itself until the end of simulation time. We got through this algorithm some results for delay and number of stops. Firstly, the delay I presented in the left side, you see the average delay for bicycle with different interval length. we have defined interval lengths from 90 to 720, and you see also the results of current state. For bicycle, for the delay of bicycle, we saw that the maximum delay happens at current state, and the minimum delay of the new controller happens at the interval length 630 seconds. On the other hand, for motor vehicles, we saw that the minimum delay happened at current state, and the minimum delay of the new controller happened at interval length 450 seconds. So for bicycle, we saw a minimum of 28% of delay compared to the current state. However, we saw a nearly 27 maximum delay for motor vehicles compared to the current state. Now here we came to the results of average number of stops. To these results, we saw that similar trends also happen. So for bicycle, the maximum number of stops happen at current state, and the minimum number of stops of new controller happens at exactly 630 seconds. For motor vehicle, also the minimum number of stops happen at current state, and the minimum number of stops of new controller happened at interval length 450 seconds. What is interesting here is shown the bike travel time and vehicle travel time in the graphs. We also noticed that this interval length with the minimum for bicycle and motor vehicle happened within the travel time of bicycle and motor vehicle. So 450 meters, so 450 seconds for motor vehicle happened during the vehicle time, vehicle travel time, and the interval length of 630 seconds happened during the bike travel time. But why the current state has the maximum in delay and number of stops bicycle, while has the minimum that for motor vehicle? Because the current state is designed to be more responsive to motor vehicle, and the coordination of bicycle in the current state was not of the priority of the network planning. So to concise the results, we saw that the new controller strategy could decrease the delay and number of stops for bicycles. These kind of changes was significant. On the other hand, the new controller strategy increased the delay and number of stops. Therefore, the results are worsening, but this worsening is also significant. However, we saw the results is better for bicycle, is worsening for motor vehicle, but still we cannot decide what to do. So what is the measure to decide according to that? To do so, we also consider the delay and number of stops, the aggregation delay and number of stops for the whole network to make decision a bit easier. So here you see the results of the network performance. To the left side, you see the cumulative delay for both bicycle and motor vehicle. To the right side, you see the cumulative number of stops for both bicycle and motor vehicle. Interestingly, we saw that in both graphs, we have a minimum, and this minimum happens at interval length of 450 seconds. For the bicycle delay, for the network delay, we have minus 1.62%. For number of stops, we have minus 0.04%. These kind of minimums, however, are not significant statistically. That means that delay and number of stops of the whole network is similar to the current state. So by this result, we go back to the previous result we got at interval length of 450 seconds. We saw that for the bicycle, we had nearly 26% reduction of delay and 30% reduction of number of stops. At the same time, we saw an increase of 27% of increase of delay for 27% for motor vehicle, and increase of number of stops for nearly 54% for motor vehicle. And as we saw that the results of current state is similar to the results of the minimum at interval length 450 seconds, we could say that the coordination at interval length of 450 seconds could fairly change the performance of the network control in favor of bicycles, while at the same time keeping the average cumulative delay and number of stops of the network similar to the current state. And then we come up with our conclusions. The study procedure here follows a model predictive structure, which was based on stop time delay. The goal of our study was to find the optimal coordination interval in which the delay and number of stops of the network are minimized. The average travel time, we could see also the average travel time between the first and the last intersection in the network could play a key role to determine the optimum coordination interval of relevant traffic users. This approach also could show a solution to find a fair delay-based coordination between different traffic users. This study, however, was implemented in an online base. And if we could access to the data online, it's also possible to implement a live application of this procedure. And in the future, we're also interested to extend this methodology by considering queue blocking effects for different traffic users and varying traffic volumes. These are also the references. And thank you for your attention.